out in Holyoke, Massachusetts. And so just for fun, this is kind of what happens when, if any of us were actually working in Cambridge and Lincoln and so on, then you know, we also have a big network pipe that goes from kind of Cambridge, and also there's a link up to Lexington sort of area. But then anytime you type a character or do anything, it's actually 140 microseconds and kind of 280 kilometers kind of round trip to your computer and back. So it's kind of interesting to think that happens every time you're doing anything. But out in this facility, we have several MIT systems that are openly available to anybody with MIT Kerberos credentials. Those include these three kind of major clusters that I'll describe a bit. And there are also a bunch of different DLCs, departments, labs, and centers within MIT have resources out there. So if you're part of a C-Cell or a Brain and Cog project, you may have some computing facilities out there in addition to SuperCloud. So one of the ones out there is this engaging cluster. I think some of the people in the class have used engaging. Engaging has quite a lot of things in common with SuperCloud. So again, sort of things we're talking about here map fairly well over to other systems as well. It's a heterogeneous cluster. It's kind of, rather than having a single kind of funding pool behind it, actually a lot of it is funded in a more distributed way. So it ends up with a mix of shared, openly available compute nodes that are available to anybody all the time, and then nodes that are funded by laboratories. And over time, that means they're not all identical. But it has actually kind of a nice collection of resources if yeah, you know, that you kind of want to explore it. The range of resources goes from, you know, nodes with just 32 gig of memory up to about 1.5 terabytes. There's about 70,000 cores, and there's a range of different generations of GPUs. Most of the really old GPUs are gradually fading out of the system. Just like with the SuperCloud, we have these systems mostly have some sort of terminal access through SSH, or most of them also have a web portal these days. And you'll find this on quite a lot of kind of open academic computer systems. A lot of us run this portal software called Open on Demand, which is a bit more busy. The screen is a bit more busy than the say the portal on SuperCloud. But if you click enough, you'll find pretty much the same sorts of things under there. So Jupyter Notebooks, RStudio, MATLAB is on Engaging. You can also quite often on these systems launch desktop kind of X-Windows based desktop. So so that's one system that is available, and I've put some links there so you can explore it. Another one that is more interesting in some ways and kind of raises some interesting kind of computing kind of factors is we also have a Power 9, IBM Power 9 based cluster out in Holyoke. So that's a Power 9 is a different sort of CPU, and in the days when I was learning computing, if you said it was a different sort of CPU, people sort of knew what that meant. But in this day of kind of everything being in the cloud, people are never really sure. But that means it's actually, if you go and try and run things on this computer, then typically you may not find that they're already recompiled C or C++ or Fortran codes for them. You may actually have to compile stuff yourself because it actually uses a different instruction set. It supports a lot of standard Python codes through, you know, Conda channels. We haven't really looked at Conda yet, but you know, sort of standard software stacks, and then Octave and Julia. But one of the side effects of this being like a Power 9 system is at the moment we don't have any R software available on it. It's an interesting system because each of the nodes, all of the nodes, has 1 terabyte of memory. So for people with very large memory problems, it can be a useful resource. And then the nodes also have 4 of the same sort. I think they're pretty much similar GPUs to the ones in SuperCloud. So they're 32 gigabyte, these Volta V100 GPUs. It has the same sort of portal stuff hanging around on it. As I say, it doesn't have RStudio and things like that. It's one nice feature of it is very similar And this is really for people who get into very large computing. It's very similar to the Summit system, which is kind of one of the US's fastest supercomputers. So, and again, it's kind of open to anyone with an MIT Kerberos ID. One interesting thing about these resources, which we like to kind of tell everybody about, is that they're very green. Actually, we're very proud of how green things are out in Holyoke. So it turns out that Holyoke has, a lot of its power is from either hydro, solar, wind, or nuclear, so non-carbon kind of sources. And with this Satori cluster about, whereas November 2019, we actually entered it into something called the Green 500 contest, and we turned out we got a fourth place in terms of power efficiency, in terms of kind of number of floating point operations per watt of electricity used. But we also did some back of the envelope calculations, or I did, based on that, which showed, and I was very struck by these, so I love this picture. I think it's slightly debatable, but if you took this system and you estimated kind of running this benchmark problem that we ran for which runs for a few hours for this kind of power efficiency measure, imagine running it for a year, that uses a certain amount of energy. You can translate that into, how many tons of carbon, or I'm not sure, it probably is a ton of carbon over a year. That corresponds to, and you can then kind of think of, that amount of carbon in terms of trees. And so the number of trees that kind of corresponds to is over a year would be about 3 largest trees. So I went through the exercise of doing this for typical computers in what's called the top 500 list, which don't all enter this kind of green 500 thing, but a lot of them, or a number of them, give the amount of power they use to do a certain benchmark, so you can kind of compare them. And my conclusion was actually the typical computer on there is almost 50 times, more. I can't count the number of trees, but it has a much larger carbon footprint. And this comes from a number of things. So, the Holyoke facility where we run things, as I say, has a lot of it's like 97% renewable energy sources. I think it's gone down a bit, but it's still, whereas the typical US mix is not like that. But also from the, making sure your programs are optimal on the machine and so on. So, so this is my kind of back of the envelope calculation, but you can actually then ask, as I say, if you take a typical HPC center, 100 kilowatt hours for, a year, at some level of kind of thermal efficiency, and at a typical number of how much performance per kilowatt you get, you end up with something like 300 trees for some, typical benchmark running for a year. Nobody runs these benchmarks for a year, so they're not really burning through that much electricity. But whereas, if you take the facilities we have, and this is true of SuperCloud as well, really, we are very green. So we like to tell people about that. So I just thought I'd throw that in there. I know these, I guess, there's the other interesting thing here. There's just, these show some of the calculations you have to do this. So you have to actually know what is the, how many kilograms of carbon go with a typical kilowatt hour, but you also have to be able to estimate how much carbon there is in a tree. So I found a nice little app that tells you that. So anyone who wants to do that. Okay, going back to other MIT resources. So the other things that I thought were worth knowing about, there is a older cluster called C3DDB that we have, which has a bunch of GPUs. It doesn't have a portal access. It's kind of reaching its end of its useful life, but it's still a resource. It's really open to everybody doing life science in a very flexible definition of the word. Due to funding, it's kind of meant to be life science related, but it's very broad. And one other thing I thought I'd mention locally is we have a storage cloud resource. So it's not as relevant to the actual class topic here, but it is relevant to people actually getting work done, especially if you're a group that turns out to have large storage long-term needs, so places to kind of put stuff cost effectively for a long time. And on the right here, I've just shown this is being installed out in the Holyoke facility at the moment, but it's actually a tape robot facility that will allow us to actually store up to 130 petabytes of information in sort of archival form. And the goal is to provide, some sort of low-cost storage for a number of very large brain, physics, some in the ocean sense world, and some in there's some other groups in biology that have cryo-EM electron microscopy. But it's a generally available facility. There is a fee associated with it, but it's just something I thought it's useful to know about. So beyond MIT, I'm just glancing at the time, there are a number of free national resources, free to the users. Obviously, they cost money. The taxpayer is picking up the bill. So XSEED is one of these. I don't know if you haven't heard of XSEED. It's a NSF kind of meta kind of effort around supercomputing. So there are a number of different systems involved in it. But again, when you look under the hood, they're similar in cluster style to supercloud. So all the things you're learning here kind of map to some of these XSEED resources. Lauren and I are both what's called campus champions within the XSEED program, which doesn't mean much except that we can provide small credits to people who want to try set up resources there. For any real use of these resources, and this is true of all of these free resources, you need to write some actual application, and then there's a review and so on. So there's a bit more inertia to actually using these. Another interesting resource is Frontera, which is kind of another NSF resource that's for very large problems. And then I just put here, there are a number of links to the Department of Energy, NASA, and the DoD actually have resources that similarly are cluster resources that should you kind of outgrow the sorts of things that we have locally, these are all available. I would say all of them are, when you look under the hood, have these same sort of scheduler, shared node abstractions. And so lots of the things we're talking about here can be kind of mapped to these. Applications for resources can be a bit of an annoyance, which is why it's nice to have some of these local facilities that we can actually get work done. And the system operations can somewhat be biased sometimes towards bigger workloads, but that's not as true these days as it used to be. It used to be that these systems were very proud of just running big kind of fluid simulations, but in the era of machine learning and AI and things, they kind of realized that they need to support a much more diverse need of workload. So see what else I have. Then a lot of people actually do use commercial cloud services. You can also even configure Slurm cluster portals on cloud services, but on the whole, you need to do this yourself. They're all kind of self-service facilities. Amazon, Azure, Google all offer kind of free credits. Some of them offer kind of, again, data storage for community data sets, which is free or can be free for a time. So those are also useful resources. Other things we see people using are things like CodeOcean and Google Colab. These are more lightweight things where they're just virtual resources out there where you can create a Jupyter Notebook-like portal environment. And for kind of modest scaling, short projects where you're happy to be self-service. Again, we see a lot of students just using this for kind of, getting projects done, testing things out. They're trying to also be a place for publishing enduring examples for sharing. So I've been trying that. This is something I saved there about a year ago, but in fact, when I tried to show that it was reproducible yesterday, it didn't work. So, we're still all learning how to do reproducible research. I didn't get it. I was hoping to actually be able to show it that it was reproducible today, but clearly something has changed in their system. So, and then what else do I have? I think then there's a little bit, just a couple of things looking forward to the future. We have a new AMD cluster coming online with like 160 AMD GPUs. So these, kind of the AMD is another computer company. These are counterparts to the NVIDIA GPUs that are in SuperCloud and the Satori system. These will also be, this will also be a Slurm-based system with portals and SSH and all the usual stuff. It, interestingly, just like Satori is a little bit like the current largest US system. This system has the same family of GPUs as what we believe will be in the next generation of super large system being built in the US, which is a thing called Frontier, which is going to go down in Oak Ridge, and it's supposed to be what they call the first exascale, or potentially it'll be the first exascale system in the US. This has 160 GPUs. Nobody quite knows the exact specification of this very large system, but it'll be maybe tens of thousands of GPUs of some sort and a very large electricity bill. And then only in terms of other future things, these are all aspirational. None of these have really taken off fully yet, but we are having ongoing efforts to raise funds for the next generation of super cloud-like system. And we have some presentations around that we give to people. There is an interesting activity called the Eastern Regional Network, which is trying to, again, raise resources to build out more infrastructure around down the East Coast, kind of from New Jersey up to Maine. And then I myself are involved in, many ongoing efforts to create, and this class is kind of part of that, create a new generation of what we call bilingual researchers, at least in the Schwarzman College, they call it that, which is, people who speak a bit of domain science, but also speak a bit of computer science, AI, machine learning stuff. So there are a number of efforts. So, in top, these are all kind of physical infrastructure things, but they're also looking forward. We imagine growing classes like the one we're having here to really kind of make sure, as the infrastructure grows, kind of the human capital is also growing. So, so that's kind of a quick overview of all the things that are in the orbit around supercloud. So I hope that was interesting for everyone to hear. I guess my meta message from this is just, once you've mastered these things, if you get really into this, there's a lot of other exciting things you can start to do and get well beyond kind of the things you do in this class.